What if the most famous picture ever taken of a planet is actually hiding the biggest secret in the solar system? I know that sounds like a movie trailer, but stay with me, because there is a photograph, a real one, captured by the most powerful space telescope humanity has ever launched, that scientists are quietly calling a warning. Not a postcard, a warning. And the reason why is about to shake 40 years of textbooks. Before we go any further, if you love stories about space that most people never hear, hit that subscribe button and turn on the notification bell. I drop videos like this every week, and you will not want to miss what is coming next. And if this one earns your respect, share it with one person who still thinks they know everything about our solar system. Now let's get into it. The picture in question is the James Webb Space Telescope's view of Uranus, released to the world in December 2023. And on the surface, it is pure magic. A pale blue world floating in the black. A set of rings so crisp and so clear they looked almost painted on. A bright glowing cap at the top of the planet that seemed to shimmer like a crown. News outlets called it stunning. They called it breathtaking. They called it the best look we have ever had at the seventh planet from the sun. And all of that is true. Every single word of it is true. The image really is beautiful. The telescope really is a triumph of engineering. But here's the part that almost nobody talked about. The same data that produced that gorgeous picture also produced measurements that should not exist. Measurements that do not match anything we thought we knew. And the gap between the pretty picture and the strange numbers is the real story, the one hiding underneath the caption. To understand why, you have to understand the planet itself. And Uranus is, without question, the weirdest world in our entire solar system. It is an ice giant, a class of planet made mostly of water, methane, and ammonia in frozen form, wrapped around a small rocky core, all topped with a thick atmosphere of hydrogen and helium. But that is only the beginning of the weirdness. Uranus is tilted on its side, not a little bit, almost completely. Its axis is tipped over by roughly 98 degrees, which means it essentially rolls around the sun like a bowling ball instead of spinning upright like a top. Scientists believe this happened because billions of years ago, something enormous smashed into the young planet and knocked it over. Maybe an Earth-sized object, maybe several. Whatever it was, it left Uranus permanently sideways, and that tilt changes everything about how the planet experiences time. A day on Uranus lasts about 17 hours, which sounds normal enough, but a year on Uranus lasts 84 Earth years. And because the planet is tilted so far over, each pole points almost directly at the sun for long stretches. That means the seasons on Uranus are not like ours. They are monsters. 20-year stretches where one pole bakes in continuous sunlight while the other pole freezes in continuous darkness. Then it flips. Imagine 20 years of summer that never ends, followed by 20 years of night. That is what life would be like on Uranus, if you could somehow survive there, which you absolutely could not. Now here is where the story gets strange, because for 40 years, scientists believed something very specific about this sideways planet. They believed it was dead. Not dead in a poetic sense, dead in a physical sense, cold inside, no internal engine, no leftover heat from its formation. And that belief did not come from guesswork. It came from a single spacecraft, a spacecraft called Voyager 2. Back in January 1986, Voyager 2 flew past Uranus. It was the first and only time any machine from Earth has ever visited that planet. And during that brief encounter, the spacecraft measured how much internal heat Uranus was releasing into space. The result was shocking. Uranus appeared to radiate almost no internal heat at all, essentially zero, nothing. And that single measurement became the foundation of everything we thought we knew. Here is why that mattered. Every giant planet in the solar system radiates more energy than it receives from the sun. Jupiter does it, Saturn does it, Neptune does it. Neptune, in fact, radiates about 2.5 times more energy than it gets from sunlight. That extra energy is the fingerprint of an interior that is still working, still convecting, still slowly bleeding out the leftover fire from its formation billions of years ago. Think of it like a row of houses in winter. Every house on the street is warm inside because every house has a furnace running. Except one. One house sits at exactly the outside temperature, as if its furnace went cold centuries before its neighbors did. That is what Uranus looked like for 4 decades. The one house on the block with no fire, the only giant planet that had somehow lost its internal engine. And that is the story we were all told. Uranus is the odd one out. Uranus is the boring one. Uranus is the dead ice giant. Textbooks repeated it. Documentaries repeated it. Every model of how ice giants work was built on top of that single measurement from that single flyby. It became one of the most confident claims in planetary science, and it was wrong. Here is the thing that changes everything. When the James Webb Space Telescope turned its infrared eye on Uranus, it saw something that a dead planet should not be able to produce. The heat signal was not zero. It was small, yes, but it was structured. It had patterns, warmer regions and cooler regions spread across the planet in a way that only happens when something inside is actively moving heat around. A truly dead interior would radiate flat and even. This one does not. It looks like a planet with something stirring beneath the surface, something our instruments could not see until now. And it was not just the heat, it was the rings. Uranus has 13 known rings, and Webb captured them in a detail that had never been achieved before, including the faintest one of all, a ghostly band called the Zeta ring, so thin and so diffuse that it had practically vanished from every previous image. Webb made it visible, and some of those rings were glowing at wavelengths that icy debris of the composition we assumed should not produce. Something in the chemistry of the rings does not match what we thought was there. And then there is the atmosphere. Remember those 20-year seasons? Our models predicted a certain rhythm driven by that cycle, a slow, predictable dance of sunlight and shadow. But Webb is showing seasonal changes running faster and more chaotically than that rhythm allows. The weather on Uranus is not behaving like the weather on the Uranus in our textbooks. And the bright polar cap that makes the planet look so beautiful in that famous image? It is changing too. It is brightening near the pole in ways that suggest the atmosphere is responding to something we do not fully understand. Now, before I go any deeper, I want to pause here, because what I just told you deserves a moment of your attention. If you have made it this far, you're exactly the kind of person I make these videos for, someone who wants the real story, not just the pretty pictures. So if you are finding value in this, do me a small favor, like this video. It takes 1 second, and it tells the algorithm that deep space stories matter. And if you are not subscribed yet, now is the perfect time to change that, because I have a whole library of videos just like this one waiting for you. Now, let's keep going, because the story gets even stranger. Here's the uncomfortable truth. There are 2 ways to explain what Webb found. The first is that Voyager 2 caught Uranus during some kind of brief, unusual state back in 1986, a temporary condition that we mistook for a permanent one. The second is that Uranus has always been more active than we thought, and Voyager's instruments were simply not sensitive enough to see the signal at the level Webb can. Either way, the conclusion is the same, and it is deeply uncomfortable. The classification we have been using for 40 years was built on a measurement we did not have the sensitivity to trust. And that raises a much harder question. If we misread the internal state of a planet in our own solar system, using a probe that flew right past it at close range, then what confidence should we have in any measurement of a planet we have never visited at all? Think about that. Because it gets worse. Voyager 2's encounter with Uranus lasted about 6 hours of close approach. 6 hours. That is it. Every diagram of Uranus's interior, every calculation of its magnetic field, every model of its rings, every estimate of its atmosphere, all of it has been built from data collected during those 6 hours, 40 years ago. No orbiter has ever gone back. No lander, no atmospheric probe, nothing. In all of human history, we have spent 6 hours looking closely at this planet, and then we built textbooks around that glance. Put that against the other planets, and the gap becomes almost embarrassing. Mars has been watched continuously by orbiters since the 1970s, with multiple rovers driving across its surface right now. Jupiter had the Galileo spacecraft for 8 years, and now Juno is still circling it today. Saturn had Cassini for 13 years. We watched Saturn's seasons change. We dropped a probe onto its moon Titan. Even Pluto, a dwarf planet at the very edge of the solar system, has better high-resolution surface data than Uranus because New Horizons flew past it in 2015 with better instruments than Voyager carried. A dwarf planet on the frozen outskirts of the solar system is better characterized than the 7th planet from the Sun. Let that sink in for a moment. And here is the part that makes the crack even worse. The Voyager 2 flyby happened during Uranian southern summer when the planet's pole was pointed almost directly at the Sun. That is the most atmospherically abnormal season Uranus has. Because of that extreme tilt, the planet spends 20-year stretches with one pole roasting in continuous sunlight and the other freezing in darkness. And the flyby caught it at the peak of that skew. We built our understanding of normal Uranus from a snapshot taken during its least normal moment. The model is not just built on limited data, it is built on limited data collected at the worst possible time. This is what fragile science looks like. Not fake science, not bad science. Fragile science, science that was the best anyone could do with the tools they had. Science that got treated with more confidence than the evidence actually supported. And science that is now being tested by an instrument sensitive enough to reveal how thin the foundation really is. Now here is where this story stops being about one planet and starts being about the entire galaxy. Because the most common type of planet in the universe is not Earth-sized. It is not Jupiter-sized. It is a category astronomers call sub-Neptunes. planets that sit between Earth and Neptune in size, small ice giants. And here is the staggering part. We have exactly 2 examples of this type of planet in our own solar system, Uranus and Neptune. And we have barely visited either of them. The Kepler Space Telescope launched in 2009, TESS launched in 2018. Together with Webb and ground-based follow-ups, they have detected thousands of planets around other stars. And the single most common type they keep finding is sub-Neptunes. That is the most common planet type in the galaxy. And our entire understanding of it comes from 2 worlds we have barely touched. Which means every conclusion astronomers draw about sub-Neptunes, every estimate of their atmospheres, every calculation of whether they could hold liquid water at any depth, every assessment of their potential habitability, is extrapolated from what we think we know about Uranus and Neptune. And what we think we know about Uranus, Webb just told us, is wrong in ways we have not fully mapped yet. So think about what that means the next time you read a headline that says astronomers have found a potentially habitable world 40 light years away. That assessment is built on models. Those models require assumptions about the interior structure, the heat budget, and the atmospheric behavior of ice giant-scale planets. Those assumptions come from Uranus and Neptune. And those assumptions are now standing on shakier ground than the headlines suggest. The confidence in those announcements is borrowed confidence, and the loan just came due. Imagine trying to build a global weather forecasting system by studying one single storm, once in 1986, for 6 hours, during that storm's most unusual season. Then imagine using that forecasting system to predict storms on every continent for the next several decades. You would produce predictions. They would sound authoritative, and you would have very little basis for trusting any of them. That is roughly where we are with sub-Neptune exoplanets. Not because scientists are careless, because the physical constraints of studying distant planets are punishing, and the field has had to work with what it has. But the work with what you have era is ending, because Webb is now producing data sharp enough to expose exactly where the assumptions were thin. And that brings us to the part of this story that is not about physics at all. It is about money. It is about timelines. And it is about whether we will actually do anything about what we have just learned. Because here is the paradox. Webb's discovery increases the scientific urgency. The scientific community knows it. In 2023, the Planetary Science Decadal Survey, the closest thing this field has to a consensus roadmap, written and reviewed by the community itself, named a Uranus orbiter and probe as the top priority flagship mission for the next decade. The estimated cost is roughly $4.2 billion. The estimated time from development to arrival is more than 20 years. And there's a narrow launch window in the early 2030s, when a Jupiter gravity assist could help a spacecraft reach Uranus. Miss that window, and the next viable trajectory pushes arrival into the 2040s or later. A slipped launch does not cost you months. It costs you a decade. And that is before you even start building the thing. Uranus sits about 19 astronomical units from the Sun. Sunlight there is roughly 1/400th of what a spacecraft receives at Earth. Solar panels are effectively useless. You need a nuclear power source, which means plutonium-238. And here is the problem. The United States allowed its supply of plutonium-238 to run down for decades, and only recently restarted domestic production. Stockpiles are limited, and every mission that needs this fuel draws from the same constrained pool. Then there is communication. The round-trip radio signal to Uranus is roughly 5 hours and 20 minutes. That means every command you send arrives more than 2.5 hours after you transmit it, and any response takes another 2.5 hours to come back. There is no real-time operation of a Uranus spacecraft. By the time you know something went wrong, it has been wrong for hours. Then add thermal management in an environment approaching absolute zero. Then add mission lifetime, because the whole system has to survive a multi-decade journey followed by years of active operation. Then add budget survivability, because a mission that takes 20 years from approval to first data has to outlive multiple presidential administrations. Every single axis multiplies the difficulty. This is what scale rupture looks like. A Uranus mission is not a bigger Mars mission. It is a fundamentally different class of engineering problem. The window is narrow, the cost is enormous, and if it closes without a mission committed, the next honest look at Uranus happens after most people watching this video are gone. Now, I want to take a quick break here because what I am about to tell you is the part that almost nobody talks about, and I want to make sure you're still with me. If this story is grabbing you the way I think it is, you can help me keep making it. Subscribe to the channel and hit the bell so you never miss a deep dive like this one. And if you have a friend who loves space, send them this video. The more people who understand what is really happening out there, the harder it becomes to ignore. All right, back to the story. Here's the uncomfortable reality of how big science actually works. The funding system that would have to turn this urgency into a real spacecraft does not respond to scientific urgency. It responds to political will, budget cycles, and the presence of an unoccupied slot in the mission queue. And right now, there is no unoccupied slot. NASA's flagship budget is already fully committed, the Mars sample. Return mission has experienced significant cost overruns and schedule delays. Europa Clipper, which launched in October 2024, is now in its cruise phase and will require operational funding for years. The Artemis program, the return to the moon, is consuming a substantial portion of NASA's human spaceflight budget. There is no unclaimed line waiting for a Uranus mission. Compare that to Cassini, the mission that transformed our understanding of Saturn. Cassini was first proposed in the 1980s. It launched in 1997. It arrived at Saturn in 2004. And it operated until 2017. That timeline, from initial proposal to the end of the mission, was almost 35 years. And it only happened with strong political and international backing. NASA and the European Space Agency partnered on it. Congress supported it across administrations. It survived multiple near cancellations, and it still took that long. A Uranus orbiter, starting from where we are today, would have to build political will from scratch, secure the plutonium supply, meet the early 2030s launch window, and sustain funding through multiple administrations. It is competing against missions that already have that kind of momentum. And here is the human consequence that rarely makes it into the headlines. The scientists who will design a Uranus mission are being trained right now. They are graduate students today. Some of them will retire before the mission launches. The scientists who received the first orbital data from Uranus may not have been born when Voyager 2 flew past in 1986. A single Uranus mission will span generations of scientific personnel. We know how to build it. The problem is that the institutional apparatus that would build it is not currently configured to build it. And reconfiguring the apparatus takes time we may not have in this launch window. Now, here's the part of this story that is not about physics and not about money, but about something even more human. It is about how this discovery was presented to you. When NASA released that beautiful image of Uranus, the framing was warm, celebratory, and short. First infrared view of Uranus. Rings never before captured this clearly. A triumph of the telescope. Every outlet ran that framing. And none of it was wrong. It was just incomplete. Because the same data that produced the photo also produced measurements that do not line up with anything we thought we knew. Why the gap? It is not because anyone is lying. It is because the incentives are structured a certain way. Public funding for space science depends on public excitement, not public alarm. The image that goes viral, the caption that gets shared, all of it has to feed the machine that generates political support for the agency's budget. Stunning new image of Uranus feeds that machine. The foundational model of ice giants may need to be rewritten, does not. It might even damage the machine because it invites uncomfortable questions. Why did NASA not know this earlier? Why is the follow-up mission not already in development? Are the agency's current priorities correctly ordered? Career scientists know this. Saying we were wrong for 40 years in public does not invite budget increases. It invites budget scrutiny. And scrutiny in the current fiscal environment is dangerous. Any admission of error can be weaponized. So the safer move is to frame the discovery as a triumph of the instrument, which redirects attention toward Webb's success and away from the gap in the underlying science. International partners share missions too. When agencies collaborate, disagreements about interpretation get smoothed over for the sake of coordination. Nobody wants to be the partner who broke the messaging discipline, so the joint statements stay measured, and the internal debates about what the data actually means happen in specialist journals and private conferences, well below the threshold of public attention. This is not a claim that anyone is behaving badly. It is a claim that institutional communication is optimized for continuity, not disruption. And when the underlying data is disruptive, the messaging lags the science, sometimes by years. What is being underplayed, specifically, is the degree to which Uranus-based assumptions propagate into exoplanet habitability estimates, the narrowness of the launch window for a follow-up mission, and the fact that the scientific community privately treats this as urgent, while the public framing treats it as delightful. The image is real, the wonder is real, and the gap between what scientists know and what the public is told, that is real too. Here is the widest frame. Webb's Uranus image is not primarily about one planet. It is evidence that our confidence in settled planetary science is systematically overstated, and that the tools we now have to observe are outrunning the tools we have to explore. Think about what Webb can do. It can resolve atmospheric features on planets in our own solar system that ground-based telescopes could not touch. It can detect chemical signatures in exoplanet atmospheres light years away. Every month, it produces observations that raise legitimate scientific questions, and those questions are accumulating faster than mission architecture can respond to them. If Uranus, a planet in our own solar system, can hide an active interior from us for 40 years, then our confidence in every unvisited world is proportionally weaker than we admit. Neptune has been visited once. Triton, its largest moon, which shows evidence of possible subsurface activity, has been visited once. The Kuiper Belt objects have been visited once by New Horizons, and only Pluto and Arrokoth got close-up looks. Everything else is inferred. And Webb keeps producing anomalies. Its observations of Titan have raised new questions about atmospheric methane cycles. Its exoplanet spectra have revealed chemical signatures that do not fit current formation models. Its deep field images have shown galaxies at redshifts that challenge assumptions about the early universe. Every one of those is a legitimate discovery. Everyone, in an era when we could mount responsive missions, would demand a follow-up. Most, in our era, will not get one. We are entering a period where observation dramatically outpaces exploration. We can see mysteries we cannot reach. That is a new condition for astronomy. And it is uncomfortable because science depends on the ability to test hypotheses. And if the only test available is another mission that will take 20 years and $4 billion, then most of those hypotheses will remain untested for a generation. For the first time in modern astronomy, our best instruments are producing more legitimate questions than our best missions can answer within a human lifetime. Compare this to an earlier era. In 1610, Galileo pointed a telescope at Jupiter and discovered its 4 largest moons. That observation broke the geocentric model of the universe, and it took nearly 400 years for a spacecraft to arrive at Jupiter and study those moons in detail. Civilization, back then, had the patience, or the slowness, to wait. We are now in a Webb era version of that same gap. Our instruments are showing us things faster than our missions can catch up, and we do not have 400 years of civilizational patience the way earlier eras did. We have decades, maybe. So here's the verdict. Uranus is measurably warmer inside than dead ice giant physics allows. The rings, the atmosphere, and the thermal profile do not match 40 years of modeling built on a single 1986 flyby taken during the planet's most atmospherically abnormal season. Every follow-up option requires launch windows, funding, and political continuity that are not currently secured. The exoplanet science that shapes humanity's picture of habitable worlds elsewhere is standing on the same shaken foundation. And the institutional messaging is systematically softer than the underlying data warrants, not because anyone is lying, because the incentive structures reward reassurance over accuracy. The comfortable interpretation of Webb's Uranus image is that it showed us something beautiful. The honest interpretation is that it showed us how much we had assumed and how little we had verified. Both interpretations use the same photograph. Only one of them looks at the caption underneath the caption. If you have watched all the way to this point, you are part of a very small group of people who care about the real story of our universe, and I would genuinely love to hear from you. Drop a comment below and tell me whether you think we will make it back to Uranus before that window closes. I read every single comment, and your thoughts honestly shape the videos I make next. And if you want to support this channel in the simplest way possible, hit that like button one more time and share this video with someone who needs to hear it. Now, let me be clear about what I am not saying, because the misreading matters. I'm not saying space science should stop. I'm not saying that NASA or ESA scientists have failed. I'm not saying that Webb was a mistake or that the mission concepts on the table are unworthy. I am saying the opposite. Webb is doing exactly what it was built to do. It is finding the places where our assumptions were thinner than our confidence. That is what a great instrument does. The problem is not the instrument. The problem is what comes after the instrument. The mission architecture to answer the questions Webb has raised still exists on paper. The launch window for a Uranus orbiter is still barely open in the early 2030s. The scientists who could design and build the answer are alive right now, working today. Some of them might be watching this video. Whether we act inside that window is not a scientific question. The scientific case is made. It is a civilizational question. It is a question about what a society chooses to fund, what it chooses to prioritize, and what it is willing to wait for. That first sharp Webb picture of Uranus, the one with the rings glowing in infrared, the one that got called stunning across every news outlet. Read carefully is a warning. A quiet one, delivered in the polite language of science, but a warning. Webb did not just show us Uranus, it showed us the size of what we chose not to look at, and it is asking, without saying it out loud, whether we are going to keep choosing.